Okay. So, again, thank you for coming. That is the last lecture in the series. I hope you enjoyed the experience, and we will do something else next time if we will be motivated enough. Sure. So, yeah, I will give second example on ray inequality. And this example is quite cool. And it's also quite recent. Oh, it's almost research level stuff. And I've heard this example at Stiklov, how it's called, St. Petersburg branch of Stiklov Institute 2 years ago. It's like one of the best Russian mathematical organizations, universities. And okay, example 2 is localized modes in a joining of 3 waveguides. Modes, probably I can say it like this, triple joining of waveguides. So, what structure I have in mind? We will try to draw it nicely. So we have 3 waveguides, and I was trying to draw a picture with symmetry 2 pi over 3. So this distances are 1. This thing is equilateral angle. And again I have Dirichlet boundary conditions. And one example. If I put my coordinate system if we put it like this, later I will use a different one. But anyway, what we know about such a waveguide? you know that modes in each waveguide will look like this. That we discussed a couple lectures ago. So what does it mean if k is less than pi? Then we don't have any propagating waves in our waveguide. So probably then you can guess the idea. What I will try to do next, I will try using Rayleigh inequality, I will try to show, and I will succeed, that we have a localized mode which localized around here. And for this, I need to build a test function for which the value of Rayleigh or quotient will be less than pi. Then I will prove that such a solution exists, and then I will prove that a solution with eigenvalue less than pi with wave number less than pi exists. And then this solution should be localized by definition, because it couldn't propagate in each section of waveguide. Nice idea. Good. Yeah, and this result was presented by great Russian scientist Sergei Alexandrovich Nazarov. I had the pleasure working with him, and I heard this. I was joining online, but there is actually a recording of this talk. But you know, this recording or is in Russian. But now I am starting to think that it might not be a useless information for you, because maybe you can feed it into ChatGPT. Now they're doing auto-dubbing, and this auto-dubbing seems to be getting better and better. But I don't know whether you can do it with like video file with a given one. Anyway, I will explain everything here, so you don't need to watch this recording, but you can appreciate him. So, okay, so we are building some test function utility, and here we have a slight difference with the thing we discussed last time, because last time we were discussing resonator with like finite area. So now we need some kind of radiation condition, and of course our test function should exponentially decay at infinity. And we will try just to build, so it should decay here, here, and here. And it will be, you know. And okay. Step one, I will consider u tilde x symmetric with respect to rotation. Okay. And also, don't remember why, but you know, I was preparing this lecture on my way to elasticity day, so there could be some things. So you should pay attention. Otherwise I can pick it. I will put my x-axis here at the center. And if I put it here, the mode that satisfies will be the cosine. Okay, just how I do it. And since I have a rotational symmetry, I will consider only 1/3 of my system. So I will consider this bit and this bit. So I building my function here, and then I just multiply it by 3 and get it everywhere. I will just annotate. But I will just integrate all my functions here, and by multiplying by 3 I will get a Rayleigh quotient. Okay, so let's try to build it like this. Of course, there is not much reason to ask me how to choose the structure, because I don't know. It kind of makes sense, we can discuss it a bit, but it's of course a game of guessing at this point. So this bit is for this small triangle, and this bit is for waveguide. Okay, this structure more or less makes sense. We just take a decaying wave. We have some parameter. We will choose this parameter later. Then we will kind of optimize this parameter so our Rayleigh quotient is less than pi square. And for this, okay, he takes some standing wave. So he took some standing wave here, so it's like a way to go. But this is a valid test function. This function definitely belongs to Sobolev space. You know, we have first derivative, and what's it? Exponentially decays at infinity, and it also satisfies boundary conditions. So we cannot choose an arbitrary function. This function should satisfy boundary conditions. Okay. So, and let's, before starting to integrate, so d is to be defined. And denote by delta this area and by this side, this part of it. That's just my notation. And okay, that's it. Now we can compute our Rayleigh quotient. Will be compute so from the last lecture we defined okay. And I will rewrite it, so I will just estimate it for this bit like this. And a bit of algebra. So we just substitute this function and a gradient of this function and I integrate it over the triangle. And I did it. It's not very hard. The same as the function itself.
Did you define the integral and the denominator just in neutron, or should it be both?
Yes, it should be. Yeah, of course. Yes. Like this. So first we can compute this ratio just to see, because here we don't have any free parameters, and if this ratio is bigger than pi, then we have then pi squared. And this one is less than pi squared. So I suppose what was Nazarov doing, he was considering test functions or in the triangle and finding a good one that will satisfy this bit. And then tuning this parameter, you can fit the rest. And this function, it's so the rest bit is even simpler to compute because it's just a nested integral. And here is the result. then we have an expression for R over D, and we can build it as function, just plot it on MATLAB as function of D. So the graph looks like this. This line is square, and this thing happens not exactly but around 1. So we can take, for example, D equal to 1 or any T in this domain. And did the computation, and it will be from R of 1 will be around 9, which less than pi square because it's 10. Oh, and that finishes the proof. And I don't know whether I should. So you can just open console, state a problem, or do like your own thing, and find the first eigenmode. In this mode, we'll look and to be honest, when you do such a problem in console, you can, for example, put some ends to your waveguides, and these ends actually won't affect the solution much because we have exponential decay, just nothing reflects back from it. But if you fancy, you can put of course some condition. This mod will be symmetrical and it will be localized, exponentially decaying here. It's like one big node here and decaying exponentially in all 3 directions. And this is quite a nice thing to prove because there is like no other way to do it. And that's something that you might not expect by default. Because like usually if you consider such a problem, you will think, okay, something propagates here, something reflects, but something can stay here also. So, and it means we have some discrete spectrum in this problem. But listening to your talk yesterday, I don't know whether it's an exceptional point of some problem or not. But it's, I think it's not, but it's like isolated point of this problem. It's, you have your dispersion diagram and you have one additional point.
Yeah, like the talk from the German guy also.
Yeah, this type of thing.
Monte, yeah?
Yeah, multiplicator.
Yeah.
Okay, that's it. That finishes the bit about Rayleigh inequality. Do you have questions? Are you satisfied as me? As I am satisfied with this. And if somebody ever will tell you that functional analysis is useful, you know at least one application. But the problem is that I also know only one application to wave theory, and I'm not sure whether it's useful in any other sense, apart from rigorous mathematics. So our next topic will be so I will considering the following equation. We can consider rewards, but I will consider what usually people consider here. And I will say probably a couple of words. First, I will write an equation. It's almost eigenvalue equation. And my notations will be first like this. And if we hadn't had this bit, we would have just got Grigor's equation. And here I consider a 2D problem. So this is a pair of variables. Now I want to use this notation. I don't use x and y. I will use x1, x2 just for the sake of compactness. And epsilon is small parameter. And this lambda constant. And if we being more up, and the last thing, the Q is periodic. And for example, if it was like a solid sheet, like a sheet of metal, then Q would have been shear modulus, and lambda would have been omega squared. And this thing I also probably should clarify. So it means that we have a periodic material with its properties that change in periodic. And we have directions of periodicity. And of course this is So this is like a periodic material, very periodic one, but it's the periodicity is very small, so it's periodic in epsilon. So its properties changes, they like change periodically on a very small scale. And for example, it could be a sheet of metal with periodically changing shear modulus. For example, you put something inside, like so, some small bits of another material. But here, for simplicity, like I won't be thinking that I will think that this function is continuous. So the properties, they change continuously. Since this procedure can be generalized for abrupt changes, then you kind of have a sheet of metals where you just cut holes periodically. And this is type of material we want to study. What's the problem with this equation? You can, if you have a simple geometry, you can try them to solve it analytically. But if you don't, you usually will use something like finite element method. And the problem with finite element method, that if you want to solve this problem directly, and you have many cells, you need to discretize on each cell. So you will need a lot of finite elements. And then person says, okay, let's consider like long waves, and then probably we can somehow average the properties of these materials, and then we can have much bigger finite elements. So the idea behind homogenization is quite practical. You don't want to solve this problem in details. We will put some average property I instead of this thing, and then we will solve a normal finite element problem. A practical thing to do. So it's kind of, we want to build an equation for you that only describe macroscopic behavior. Okay, that's the statement. Are you fine with it? Because I understand it's a bit specific, but that's what we have. And of course it has a direct connection to metamaterials.
So you define y with respect to the small variable, right? Yeah. So it's
y. Yeah, I could have. Yeah. So that's my dependence.
Yeah.
Yeah, it's kind. Yeah, I have a periodicity with respect to small variable.
Yeah.
I can say it like this, and it's like not variable scale, but then once. So I need to make one more step to make it variable, and that's the idea of homogenization. So, and this thing is done. Homogenization is done using method of multiple scales. Have you heard about it before? You heard about it, yeah. Good. So, but anyway, naturally we discussed that first, this problem has two scales. Macroscopic, which is x of order 1 and 2, microscopic. X of order epsilon. And I want to save a bit of notation later, so I won't draw this arrow, but you should have in mind that x with a vector. Is it fine to you?
Yeah.
Okay? Because so I'm going to drawing, but x is x1, x2. And to apply this method, we introduce a pair of variables. One of this is x prime, which is equal to x, first scale. I just being very familiar. And the second one is psi, which is equal to x for epsilon. And then very obvious step. I will say, okay, we have two scales, and probably let's try to build a function that depends on them as on two different variables. That's kind of a mantra, but there is no simple way to justify this mantra with kind of general understanding. But probably for this problem in the infinite media, you can explain why. But from like a naive point of view, it makes sense. So we built a series on epsilon. Okay? And we will try to build an equation for the first term of the series. And once we did it, we can take this function and if we build all terms of our series, we will do something like this. If this type of notation makes sense to you. So we will change back to normal variables. And what else we will impose? We will additionally impose periodicity condition on each term of the series. Okay.